Hello. Today we're going to be talking about topic 2.5, applying the power rule. I'm also going to connect power rule to the concept of differentiability to topic 2.4. So I'm excited because this is going to be kind of the first big step into finding algebraic or derivatives algebraically. It's going to be the first rule that you're going to learn, and ultimately it shouldn't be too bad. Feel free to pause the video at any time or rewind or fast forward if needed. Okay, so just a review of topic 2.2 of how we found the derivative using limits. Okay, so if I were to go through this and I were to say, okay, the limit as h approaches 0 of f of x plus h, so I could say a negative 4 x plus h squared minus a negative 4x squared, careful your negatives, all over h, right? So we're just taking the derivative using limits. I'm going to then expand out that binomial. So negative 4x squared plus 2xh plus h squared plus a 4x squared all over h. And if I have the limit as h goes to 0, I get a negative 4x squared minus 8xh plus, oh, that should be a minus, excuse me there, minus a 4h squared plus 4x squared all over h. And now the fun part, guys, gone, okay? And if I divide out my h from what's left, I have the limit as h approaches 0 of a, excuse me there, of a negative 8x minus 4h. Again, I divided an h out of the remaining terms. So now if I evaluate that limit as h goes to 0, the negative 4h goes to 0, so I just get a negative 8x, and that is my derivative. Now, if I wanted to use good notation here, I would say something like f prime of x is equal to a negative 8x, right? So that would probably be better notation. All right, so we're finding the derivatives using limits. So I got one more with radicals, right? Just to kind of remind you what this looks like. We'll come back to these in a minute. But if I set up my limit as h goes to 0 of the radical or square root of x plus h minus the square root of x all over h, I'm going to use the conjugate, okay? So I'm going to say the square root of x plus h plus the square root of x all over the square root of x plus h plus the square root of x. And if you multiply conjugates together, you're just going to get a difference of squares. So x plus h minus x all over h times, don't forget that second piece on the bottom, all right? And again, I always like the fun part, cancel, right? So I'm left with a limit as h approaches 0 of h over h times the square root of x plus h minus the square root of x, okay? And I can cancel out even more. Those h's cancel. So I now have, if I evaluate the limit for what's left, I'm going to get a 1 over the square root of x plus the square root of x, which is 1 over 2 square roots of x. Now again, I ran out of a little bit of room, but I would call that f prime of x, right? F prime of x will equal 1 over 2 times the square root of x. Okay, so here's what we're going to do now. We're going to transition to, we're going to do a little exploration with graphs. So this was a little review of how to do derivatives with limits. We're going to do a little review of, graphing the derivative. Okay, now I did in a previous notes video, there are directions on how to graph the derivative on your calculator. So if you need to do that, you can, just to check. But I want you to see that this is going to be a positive slope, and I have a positive slope. It's actually a constant slope the entire time. So it's going to be a constant positive value. So if you were to take a look at this point, at any point, and you draw a tangent line, a little local tangent, at any of those points, they all have the same slope. They all have the same positive slope. So at, let's say, negative 2.5, I know I'm going to have a positive slope value. At negative 1, I have the same slope value. At 0, it's the same. Again, when you graph the derivative, right, the y values represent the slopes of the original function. So, oh, that was bad. Let me redo that a little bit. Okay. All right, that's the best straight line that you're going to get from me. Okay, so ultimately, I just get a constant function. So if you have a constant rate of change or constant slope, it makes sense that the graph of the derivative would be a constant line, right? So let's take a look at something that's not necessarily constant. Let's look at this quadratic. Now, in the very beginning, if I draw a little tangent, the slope is very, very negative. So right around the same x value, so that x value is right around negative 2, I'm going to make a point at a very, very negative value. Again, because the y values represent the slopes. So the slope of this line is negative. So therefore, I put a point at a negative y value. Now, if I go to like negative 1, right, and follow that line, it's still negative, but it's not quite as negative. So again, I don't have any specific values to go off of. So I'm going to put at another negative value. Now at the vertex, at the origin here, well, that's a little minimum. That's going to be a 0 or a horizontal tangent. So at that minimum, I'm going to be at 0. And then if I go to 1, well, this graph is symmetric, right? So if whatever the negative slope was at negative 1, I'm going to have the same value at positive 1. And then at 2, I have the same slope but a positive at 2. And I get something that is fairly linear. Okay, so the derivative of a linear graph was constant. The derivative of a quadratic graph was linear. You could probably guess, but I'm gonna go through it anyway. What's the derivative of a cubic gonna look like, right? So if I go over to like negative 2, now my graph doesn't exactly reach negative 2, but I know it's gonna be very, very positive. So if I go at negative 2, I know this is a very steep positive slope, and I'm actually gonna use a different color here, okay? Try to color code this the best I can. So it's very, very positive. Then at negative 1, okay, I know it's positive, but not quite as positive. All right. At 0, my graph quickly goes to horizontal. And then at 1, it goes positive. And then at 2, doesn't quite get to 2, but it's also back to being just as positive. Now, this is an odd function, right? So there's some symmetry here. But if you take a look at this graph, okay, we get something that looks fairly quadratic. Okay, now it's very important to note that at the origin here, I do make this a smooth curve. This is not going to have a corner or a cusp in it. Okay, it is differentiable at that point, so I don't want to make any sharp turns. But I want you to kind of take a look at what's happening from the original graph to the derivative. So the original graph in the first one was linear to a constant. Then I went from a quadratic to a linear. Then I went from a cubic to a quadratic. And that's hitting on a big idea here. And that's hitting on the idea of power rule. When you take the derivative algebraically of a polynomial or anything raised to a power, of a variable raised to a power, we don't need to necessarily use limits to take that derivative. We can use this idea of power rule. So I want to read through this mathematics with you to make sure you understand. If I have d over dx, this is the derivative. Okay, so I'm going to take the derivative of x to the n power. Okay, now what's going to happen here is if I take the derivative of that exponent is going to now become a coefficient, and my new power is going to go down by 1 degree. Okay, so that's what this part means over here. If you look, the n's all mean the same thing. So that the exponent was n, that's now the coefficient, and my new exponent is going to be -1. It goes down a degree. So take a look at example 3 here. All right, I have f of x equals a negative 4x squared. So I want to use good notation. I'm going to say f prime of x equals. I'm going to take this 2 and I'm going to drop it down. Now, when you drop it down, it's going to multiply. So that's going to give me a negative 8x to the 2 minus 1 power. Now, you don't really have to write 2 minus 1 power. I'm hoping at this point we know it's going to go down by a degree. So I'm going to say that I'm going to have a negative 8x to the first or negative 8x. And that's the derivative. So I didn't have to use limits to find the derivative. Okay? So if you take a look at example 4, h prime of x, I do the same thing. I'm going to drop this 7 down. So 7 times 9 is 63. X to now the 6th power. Now the next term, this is negative 9x to the first. If I drop this 1 down, negative 9 times 1 is a negative 9. X to now the 0 power. Now, this last term is very interesting because it's just 6. So this is like saying 6x to the 0. So if I follow the same rules, if I drop that 0 down, 0 times 6 is 0, x, and if you lower it degree, it's to negative 1. However, anything times 0 goes away, right? So if I do 0 times x to any power, that's still 0. It doesn't make any bit of difference. So if I write this, I have a 63x to the 6th minus 9x to the 0 is just 1, and we said that that last term is 0. So I would write this as 63x to the 6th minus 9. And this is my derivative. Okay? So again, I just want to kind of review power rule. Now, there are some problems that are a little bit more hidden, okay, where it's a little bit more, how do I apply power rule to them? So I want to kind of just remind you of some algebraic properties so we can apply this power rule to as many problems as we can. So ultimately, we don't have to do limits, okay? Now, you might remember number 5 from the beginning when we had to take the derivative with limits using the conjugate. I can take the derivative of this using the power rule because the square root of x is the same thing as saying x to the 1/2 power, okay? So if you do this, if I drop that coefficient or that exponent to become my coefficient, I am now going to get a 1/2 times x. Now, if you lower this by a degree, you have to subtract 1 from it, okay? So I'm going to show my work here. If you subtract 1 from that, I get a 1/2 x to now the negative 1/2. Now, you're probably asking yourself, well, that doesn't look the same as what we used to. But let's remember, it's to a negative power. So that would be like saying 1/x to the positive 1/2. And if it's to the 1/2, this is still saying 1/2 square root x. And that, ladies and gentlemen, if I scroll up, okay, is the same answer that I got when I used limits, okay? Now, when you use this power rule, you'll be able to do it a lot quicker and without having to write a limit for that, so you won't have to worry about notation as much. So I really want to encourage you guys to use this power rule. Now, if you take a look at number 6, all right, now again, this is kind of hidden. We have this rational function or this quotient of two things, right? It's written as y, so I'm going to write this in a slightly different manner, just so that we can do power rule. So I'm going to say x to the 5th over x to the 1/3 plus 2x over x to the 1/3 plus 6 over x to the 1/3. And so if I'm dividing by one term, I can divide each term of the numerator by that term. And now if I reduce that, I get x to the, and if you did 5 minus a third, okay, well, 5 is 15 thirds minus 1/3 would be a 14 thirds plus 2, this is x to the 1st, so I would now have a 2x to the 2/3. And then I have, excuse me, that looks like a little negative there. I want to get rid of that. There we go. Okay. And then I'm going to say plus 6x to the negative 1/3. So I found a way to manipulate this problem so that it is just 3 terms with 3 powers. So if I take the derivative, so I'm going to say dy over dx, the derivative of y or the change in y over the change in x will be a 14 thirds x. Now, if I lower this by a full degree, if you subtract 1 from that exponent, I'm going to remove 3 from the numerator. So I'll be at 11 thirds plus, now 2/3 times 2 would be a 4 thirds x. Now, if you subtract 1, I get a negative 1/3. And then it's actually going to be a minus here. Negative 1/3 times 6 would be a negative 2x. And if you subtract a full degree, I get a negative 4/3. Okay. Now, typically they don't really like to write their answers with negative exponents. So I would write my final answer like this, over 3x to the 1/3, and then minus 2 over x to the 4/3. But this would be my derivative. Okay. So if you look in the beginning, I found a way to write the original problem as a list of powers or separate terms. And then I could take the derivative of each of those powers very quickly. Okay. Now the last two problems here, I have piecewise function. And I don't want you to be concerned about that. Ultimately, when I do a piecewise function, I'm just going to take the derivative of each piece of that function. So I'm going to say here, f prime of x is going to equal, all right, now if I do the derivative of the first piece, 2 times 3 is 6x. The derivative of 1, remember, the derivative of, when it's just a number, when it's just a constant, it's like saying x to the 0 next to it. So the derivative of every constant is going to be 0, okay? Now, if I do the second piece, drop the 3 down, 3x squared, okay? And then the derivative of the 3 is 0. And I am going to put something like that, okay? Now, the only thing that I don't know here is do I have to put an equal to on one of these, right? So that's a question that we need to look into. And I want to know, should that derivative actually exist at at 2, right? So I'm going to do a little exploration here. I want to know, what is the limit as x approaching 2 from the left of f of x actually going to, right? So if I go from the left, that's going to be 3 times 2 squared minus 1, which gives me 4, 12, gives me 11. If I do on the bottom, the limit as x approaches 2 from the right of f of x, okay, that is going to give me 2 to the third plus 3, which is also 11. So I know it's continuous, so it does have a chance to be differentiable. Now the question is, what's the slope from the left and the slope from the right? So the slope from the left, if you take 2 and plug it into the left-hand side of my derivative, I'm going to get 12. If you take 2 and plug it into the right-hand side of my derivative, you also get 12. So you can put an equal to on there. It is going to be the same from the left and from the right. Okay, so that would apply. So I would put an equal to on that function, but that might not always be the case for all of them. Let's take a look at number 8. So the derivative f prime of x would equal, so the left side is 5 to the first. So if I drop that down, 5 times 1 is 5. Now x to the 0. The derivative of this 6 is just 0. Now I'm going to kind of sidebar over here. Square root of x plus 7 is x plus 7 to the 1/2 power. If I drop that exponent down, that's now going to be to the negative 1/2 power. And if I write this without a negative exponent, because it's negative, it would be on the bottom, and the 1/2 is a square root. So I'm going to say that my other side is 1 over 2 square root x plus 7. And this was x less than or equal to 2, and x is greater than 2. Now, I need to do a little investigation. Should I have that equal to or not? So the left side, so as I approach 2 from the left of f of x, that's going to be 5 times 2 minus 6, which gives me a 4. And the limit as x approaches 2 from the right of f of x would equal 5. I'm sorry, the square root, excuse me there, use the right sign. The square root of 2 plus 7, which is a square root of 9, which is 3. Those are not equal. So because the limit from the left and the limit from the right are not the same, I know there's a jump discontinuity. And we said in 2.4 that anytime you have a discontinuity, I know my derivative does not exist. It cannot be differentiable if it's not continuous. So to kind of just write this down so you have it, this proves that it's discontinuous at x equals 2. And because it's discontinuous at x equals 2, it cannot be differentiable. Therefore, I do not want an equal to sign on my piecewise constraints. Okay? So let's take a look at some problems here. I want to kind of pair the idea of continuity and differentiability together. Let's try to iron this out here. If I have a quadratic, okay, the quadratic has no corners, it has no cusps, it has no discontinuities. Ultimately, the interval of continuity here would be from negative infinity to infinity. There are no jumps, vertical asymptotes, anything like that. Okay. Now, the derivative of my graph or of my function, I'm going to use that power rule. So I'm going to drop the 2 down. So 2 times 4 is 8. X to the first minus, drop this 1 down. That's on the 10x, right? So minus 10x to the 0, which would just be x to the 0 is just a 1. And then plus 2, derivative of any constant is 0. So my derivative is 8x minus 10. So when is this derivative going to be continuous? Well, it's linear, right? So if I have a linear function, it's continuous everywhere. So I'm going to say negative infinity to infinity. And ultimately, if my interval of continuity is negative infinity to infinity, and my derivative exists for all of those points, then my interval of differentiability is also going to be from negative infinity to infinity. Okay? Let's take a look at the next one. So I have a radical function here, okay? And this just shifted, the square root of x minus 6, it shifted 6 units to the right. So ultimately, I know my interval of continuity is going to be from 6 to infinity. Okay? So now I want to take the derivative. So I'm going to kind of show some work here. So I have the square root of x plus 6. I can rewrite that using a power. So I'm going to raise it to the 1/2 power, right? Same thing. So if I drop that down, I get 1/2 x plus 6 to the negative 1/2. And I can write that without a negative exponent as 1/2 square root of x plus 6. Okay. Now, over what interval is f prime of x continuous? So when is this derivative going to be continuous? Well, I still have the same radical, so I still have the same restrictions. You can't have a negative inside that radical, so I know that my values have to be bigger. Excuse me, guys. I apologize. I put a plus 6. This should have been a minus 6 in here. Ignore that, right? So that might affect my intervals here. But so I know that I can't have a value smaller than 6. And because I can't have a value smaller than 6, I know my interval of where this is continuous is going to be from 6, and I can go anything bigger. However, at 6, that would make the denominator 0. If you substitute 6 into this, the denominator is going to be 2 times the square root of 0, and you can't have 0 in the bottom. So I'm going to use a parentheses there instead of a bracket. So where is this differentiable? Well, it's differentiable everywhere where the derivative exists. It's going to be differentiable from 6 to infinity, but not including the 6. And that's the part where I want you to kind of pause for a second, is because 6 makes my derivative undefined, which means if a slope is undefined, I got a very, very vertical slope at that starting point. So ultimately, we can get the interval of differentiability from looking at the domain of the derivative, okay? If I take a look at this one, right? Well, I know that this will be continuous from negative infinity all the way to 4 because all linear functions are. I also know that this radical would be continuous from 4, from 4 to infinity because 4 is defined in that. And any number bigger than 4 will still be okay for this radical. All right, now the question lies, what happens at 4? Is it going to be continuous at 4 or not? So I'm going to substitute in. I want to see, does the limit from the left equal the limit from the right? And if I do that, I get a negative 8 plus 10 is 2. And over here, I get a negative 8 times 2 is a negative 16. Those are not the same, so therefore they are not continuous at 4. So this would be my interval of continuity. If those were the same, then I would just join them together at that point. I would make it from negative infinity to infinity. I would include the 4 within my interval. But let's take the derivative of that piecewise function. And if I do that, the derivative of a negative 2x, now that's to the first power, would just be a negative 2x to the 0, because if I lower it a degree, x wouldn't be there anymore. And then plus 10, well, the derivative of a constant is 0. That goes away for x less than 4. Now, we already said that it's not continuous at 4, so it can't be differentiable. Okay, so that's why I did not put an equal to there. Now, if I take the derivative of the next piece, okay, I need a little bit of room here. But if you take the derivative of a negative 8x to the 1/2 power, if I drop that down, that's going to be a negative 4x to the negative 1/2 power. And then if you put that on bottom, I'll get a negative 4 over the square root of x. And that's going to be when x is greater than 4. Okay. Now, when is this continuous? Well, we already know it's got a discontinuity at 4. But let's explore this a little further. Let's see what's going to happen here. I know the top piece is continuous from negative infinity, I'll use red here just to keep my colors consistent. So it's going to from negative infinity all the way to 4. I know my function is continuous because negative 2 is a continuous function. However, after 4, we already know it's not going to be differentiable at 4 because it doesn't exist, or there's a discontinuity there. If I plug 4 into this, anything after 4 I think is okay. So from 4 to infinity. So what is my interval of differentiability going to be? Well, the interval of where my derivative is continuous is going to be the interval of differentiability. Okay. So ultimately, I'm trying to find the domain of the derivative, and then I'm trying to apply that domain to the interval of differentiability. All right. All right, we got a heavy hitter for this last one. It's a piecewise function, but it has 3 pieces. So what I want to do is I want to know, if you look at each of these, I have a linear, quadratic, and cubic. All of those are continuous on their own right, but the question is, will they be continuous where they meet up? So if I were to plug in a negative 3 times negative 1 minus 2 at negative 1, is that going to be the same for the the left and right side of negative 1? So if I simplify this, I get negative 3 minus 2 is a negative 5. And then here I'm going to get a negative 2 minus, I'm sorry, that should be squared. So I'll get 2 minus 7, which is a negative 5. So far, I know that this is going to be continuous at negative 1. Now let's check 3. So if I do the same thing, if I do 2 times 3 squared plus 7 times 3, will that equal 3 cubed plus 12? So if I check that out, I'm going to get 9, 18, excuse my writing here, 18 plus 21 will equal 9 plus 12. And ultimately those, I'm sorry, not 9, that should be a 27. So if I add those together, I get 39, and I get 27 plus 12 is 39. So this function, believe it or not, is continuous from negative infinity to infinity. Now let's take the derivative and let's see if that's still the case. Okay, so if I take the derivative of this, derivative of a negative 3x minus 2, so this is negative 3x to the first, drop that 1 down, is just negative 3x to now the 0 power, so there are no x's. Derivative of the 2, derivative of a constant is 0. And then the derivative of the next piece, if I drop this 2 down, I get a 4x plus 7. And the derivative of the last piece is a 3x squared, and the derivative of 12 is 0. So now I need to know, do I need to put equal to's on any of these constraints? So I know I'm at least going to use the constraints without the equal to's. And the good news is I know it's continuous at all of those points. I just need to know if the slopes are going to be the same at all of those points. So in order to determine if there's going to be an equal to, I need to know if the slope from the left and the slope from the right of those points is going to be the same. So the left of negative 1 is 3. The right of negative 1 is going to be a 4 times negative 1 plus 7. I get negative 3 equals 3. That would not get an equal to. Okay. Now, if I keep going, if I do the left and the right of 3, I'm going to say here, let's get a color, 4 times 3 plus 7 equals 3 times 3 squared. So I get 12 plus 9, or plus 7 is 19. This would be 27. Those are also not equal to each other. So that would not get an equal to. So where is this continuous? I would say from negative infinity to negative 1. union -1 to 3, union 3 to infinity. Okay, so where is it differentiable? Over the same intervals. Okay. If I'm going to clear this off so I can read this last question. So we did one of these in an earlier notes topics, finding this A and B value. Okay, I think it was like topic 2.1, maybe 2.2. Okay, I want to find the A and B so that all of these are differentiable over all x values. So there's kind of the definition of differentiability. One, it needs to be continuous. Okay, and then 2, the limit as x approaches some a value from the left of the derivative has to equal the limit as x approaches some a value from the right of that same derivative. Okay, so I'm going to use this idea. So first I'm going to check continuity. So if I do the limit from the left, and actually I'm going to use good notation here. Okay, so to check continuity, I'm going to take my time. The limit as x approaches 2 from the left of f of x has to equal the limit as x approaches 2 from the right of f of x. So if I do from the left side, I'm going to get a times 2 cubed, and that's going to equal 2 squared plus b, which gives me an 8a equals 4 plus b. Okay, and I'm going to leave that for a second. So now I want to take a look at the derivatives. Okay, now I know the derivative from the left and the derivative from the right have to be equal. So let's start with our derivative. So f prime of x is going to equal a 3a x squared, because I dropped the 3 down. 3 times a is 3a, lower the degree, and a 2x plus b, but the derivative of b is a constant. So anytime I take the derivative of a constant, it's going to go to 0. And I actually don't want the equal to there yet. Okay. Less than 2 and x greater than 2, right? Okay, so I now want the slope from the left and right from 2 to match, right? So if I do this, I'm going to try to use good notation. So the limit as x approaches 2 from the left of f prime of x has to equal the limit as x approaches 2 from the right of f prime of x. So if I plug 2 into the left of my derivative, I'm going to get 3a times 2 squared, and that's going to equal a 2 times 2. So I get 4, I get a 12a equals 4. And if you divide the 12, I get a to be a 1/3. So that's my a value. Now my b value, I can just go back up to the top here. I know 8a equals 4 plus b. So if I do 8 times a 1/3, that's going to equal 4 plus b. So I have 8/3 equals 4 plus b. And if you subtract 4, I'm going to get a negative 4/3 for my b. So there is my a and b values such that it will be differentiable for all real numbers. So when you're finding these missing values, 1, set up your limits to make it continuous, and then 2, set up your limits for the slopes on the left and right to be the same. Okay, very, very important. All right, I got a couple more here. Just a reminder of tangent lines. So I have in order to write the tangent line, I need a point and a slope. So my point is already given to me. Is going to be 1, 0. But I need to find my slope. Now the slope at that point is going to come from the derivative. So I want to take the derivative of this problem. I'm going to drop the 4 down. Gives me a negative 8x cubed. Drop the 2 down. Plus 10x to the first. And then the derivative of negative 3 is 0. Right? So that's way easier than doing limits, right? I've already gotten the derivative. You could have done limits to get there. I didn't need to, okay? I just used the power rule. So now I want to know the slope when x is 1. So I can say negative 8 times 1 cubed plus 10 times 1 gives me a negative 8 plus 10, or in this case, gives me a 2. So I have the line y minus 0 equals 2x minus 1, or y equals 2x minus 1, right? There is my tangent line, okay? Now, number 11 requires a little bit of rewriting, all right? I'm going to write this function. First, I have my point, right, at 1, 2. But I need my slope. So I'm going to write this function not as 2 over the 4th root of x cubed, but I'm going to write it as 2x to the 3/4 power, because that allows me to use power rule now. So if I drop that exponent, so f prime of x is going to equal a 6/4, or in this case, a 3/2 x, and if I lower the degree, I get a negative 1/4. I'm going to write that with the radical on the bottom. So I have 2 times the 4th root of x. And now if I want to find the derivative at 1, I have 3 over 2 times the 4th root of 1, which is just 3 over 2. So I have a point, I have a slope. I know my tangent line will be y minus 2 equals a 3 over 2 x minus 1. And again, we always want this to be y equals, so 3 over 2 x minus 1 plus 2. So that would be my tangent line, okay? Now, number 12 is asked in a slightly different way. It says, find k such that the line is tangent to the graph of the function. So this one is slightly different. I give you the tangent line, and I want to know what the function is, right? I want to know what the k value of that function was. So ultimately, I know the slope of this tangent line is a negative 2. Okay, that's what's important. All right. So what I want is if I take the derivative, okay, of this function, I get f prime of x is equal to 2kx. All right. And I know that the slope of this function, all right, is going to be a negative 2. So I want to know at what x value does that happen? Okay. Now, if I'm going to go about this, I know that this expression has to be a negative 2. But how can I get my k value? Well, I think there's a piece of, we're going to skip this question. I think there's a piece of information. I think I have to give you a point. And then you should be able to find that function. So I think I forgot to give you the x and y value. So we're going to have to take a pass on that. Okay. However, these last two should be good. Horizontal tangents. When you have a horizontal tangent, the slope is 0. Right? I want to know when that slope is 0. So if I take the derivative finds slope. Drop the power. And then derivative of 3 is 0. So now I have a dy dx equals a 4x to the third minus 4x. Now, if you have a calculator, you can set this equal to 0, and you can find the x-intercepts on your calculator. I'm going to do everything by hand. I'm going to take a 4x out. That gives me an x squared minus 1. So I have an x plus 1 x minus 1, which means my zeros are going to occur at 0, -1, and +1. So those are all the x values of where I have a horizontal tangent. Now, if you wanted to find a point or coordinate, you could plug those x values in and find the y values to the original function, and that would work. Okay, so horizontal tangents are where I have a slope of 0. So dy dx is equal to a 3x squared plus 1. Okay, again, there's a 1 in front. This is to the 1 power. So if I set that equal to 0, I'm going to have a 3x squared plus 1. If I subtract the 1, divide the 3, take the square root of it. Now, if you notice here, I get the square root of a -1/3 equals x. Now, we're not dealing with the complex plane. We don't have to deal with any i's. That's not of any issue to us. But what this does say is that because there are no real answers, there are no x values where I have a horizontal tangent. Okay, so because there were no places where my derivative was 0, just means that there are no places where I will have a horizontal tangent. Okay, that was a lot of information. All right, the big idea is I want you guys to understand power rule. Okay, but I also, through these different rules that I'm going to teach you, I want to connect them back to differentiability. I want to make sure you can find an interval of where a function is differentiable. And then lastly, I want you still to be able to write tangent lines using those rules or applying them to maybe a new context. In this case, horizontal tangents, where my slope is 0. Okay, so that's topic 2.5, power rule and differentiability. Have a good day.